Any other questions about this? Because I probably haven't done a good summary. There's a little bit more in these notes. These are from a Nature review article. These pictures. Yeah. So much like everything else that these startups are doing, these are fabricated using, I guess, fairly standard. I mean, it's on silicon or something. Somehow you make it all work. Yeah, so I don't know what this picture is. There's a better picture in the YouTube picture where you can actually, in the YouTube video, where you can actually see the Josephson junction, like much closer up. And it just looks like, so this Josephson junction is really just two wires sort of going next to each other. And it actually looks like quite a mess, but it works somehow. Okay. I don't know, any other questions? Okay. What else is there? So that's superconducting. We talked about a lot of different technologies now, at least briefly. Maybe another one is anyons, or topological qubits, which, I mean, it's a really fun theoretical topic. I could definitely talk, I could give a lecture on that if anybody's interested. This is, it's pretty speculative in the sense that nobody has conclusively demonstrated qubits, and like there's no 2-qubit topological device right now, topological qubit device right now, let alone a 100-qubit device or a 50-qubit device. But nonetheless, Microsoft has sort of gone all in into trying to produce anyon or topological quantum computer, and so that they've been really trying to deal with these. I don't know. You get all sorts of fabrication problems when you're trying to put superconductors on top of silicon, and I don't know, getting the lattices to line up, and who knows what goes wrong with this. And so they've had all sorts of experimental issues, but I think Microsoft has at least like 3 different experimental groups trying to work on this. Plus they've, the theoretical group at Santa Barbara, plus theoretical groups at Redmond, plus theoretical groups all over the world, right? So they're kind of somewhat invested. I don't know how well that's going to turn out. Probably a lot of the theory that they're doing probably could carry over to other devices. I think even some of the experiments. So the experimenters who are working on topological computation, it's the same kind of devices as the superconducting qubits. Actually, like it's exactly the same fabrication that they're doing. And so I've gone to some talks where they demonstrate, just as an example of what they've done, that they have x many superconducting qubits on their chip, but they don't really sell that publicly, because publicly they're all in on this. But if they had to, they could switch, I think.
Could you please explain what exactly is anyon topological quantum computing? Because I have no idea what does it mean.
Oh, okay, yeah. So sorry. So I should give you sort of a big picture. Or at least I can tell you the story that they say, and you can judge for yourself. So the idea is, if you look at the history of classical computing, way back when in the 1940s and 1950s, people were using vacuum tubes. It's pretty cool. You can Google up these pictures. There's a whole room full of vacuum tubes, and there's someone looking for the one that's broken, so they can replace it. They can unscrew it and put in a better one. And it's obviously quite a mess, but nonetheless, if you look at it, so who was this von Neumann back then? He was thinking about how we could make classical computers fault tolerant, how we can deal with errors in these devices that break all the time, these vacuum tube devices that break all the time. And he was also interested because he was thinking your brain is a classical computer, and it presumably breaks all the time. I mean, why would neurons be perfect? And yet we can talk in complete sentences sometimes. So he had this idea how we can deal with significant error rates, even on the order of 1% or something, per operation, and still be able to compute interesting things on the classical computer. But historically, a lot of that was sort of forgotten, because it turns out that somebody invented, what are they called? Transistors. Yeah, which nowadays you have just billions of them on your cell phone or whatever. And they're sort of inherently fault tolerant. So the noise rate per transistor is like, I don't know, it's like 10 to the minus 21 or 10 to the minus 19 or something per operation or something, which isn't necessarily that small when you have billions of them and they're operating in gigahertz. But still, it's relatively small, and you don't have to worry about these vacuum tubes failing all the time. And so a lot of fault tolerance theory that like von Neumann and others developed was never used. It's just sort of a curiosity. And so now quantum computers come along. So that's a long history. Quantum computers come along, and again we get the same issue that they're like vacuum tubes. They're extremely noisy. Error rates are on the order of 1% per gate or even higher. Hopefully we'll get it down another order of magnitude or two, but still it's extremely high. And so anyons, the story we say is that anyons are supposed to be inherently fault tolerant. So it's supposed to be the analog of a transistor, but for quantum information. That's sort of the big picture, is that we're going to be able to. Okay, so I can explain why. But okay, let me keep going. So the idea is that these are going to be inherently fault tolerant. So initially, people are going to say the error rates are going to be 10 minus 12 or something per operation compared to 10 minus 2. Okay, so much better. I think nowadays they're saying, they're tempering their expectations. So they're saying maybe 10 to the minus 6 or something like that, or maybe less than that, worse than that. But still, I mean, that's significantly better than the current technologies for superconducting qubits or something. I mean, of course, it's just wishful thinking, but that's the hope. And theoretically, these kinds of things could exist. Nobody's demonstrated it. But I mean, it's closely related to like the what's it called? The quantum Hall effect, and especially to the fractional quantum Hall effect, which is pretty well demonstrated physics. It's sensitive physics, like it's not easy to do, but it's when was the fractional quantum Hall effect? Fractional Hall effect.